Touch input devices are everywhere, but they lack tangible affordances, a fact which has inspired researchers to create new types of passive electronic inputs. Instead of having their own sensing, these manipulate the quantity sensed by the touch sensor. While this quantity is thought of as capacitance, in reality it's more complicated. Touch devices actually measure impedance, the complex resistance of the circuit created when your finger contacts the screen. Impedance, though, is not a single number. It's made up of capacitance, resistance, and inductance. While touch devices focus on the integrated quantity of impedance, LCR meters can measure these features individually. Based on this capability, we introduce Impedius, a signal space multiplexing technique. With Impedius, we can create and sense multiple static values and continuous changes on a single wire by manipulating the component values of impedance individually. Here we focus specifically on capacitance and resistance, as inductance interferes with the capacitance. For example, here we have two buttons, one with a resistive, or R, signature, and one with a capacitive, or C, signature. The attached LCR meter can detect when each is pressed. When we connect these buttons in series on the same wire, we can still distinguish which is pressed, based on whether we see an R change or a C change. This capability can be extended to multiple R and C IDs. Here, we chain together a series of blocks with unique signatures and examine the aggregated values to detect what has been added. We can also sense continuously changing values. Here, we have a 2D joystick with one dimension mapped to R and the other to C. Multiple variable components are possible within a single series circuit by creating stepped value changes of specific sizes. Inductance, capacitance, and resistance are controlled through various physical and material properties, which can guide designers to create different interactions with these signals. Using these geometric guidelines, we performed experiments on 3D printing predictable passive electrical components. We encapsulated our results into a Fusion 360 plugin to generate electrical geometry for our sample applications. Our prediction error is around 20 to 25% for C and R. But this error is correctable. For example, this slider uses R and C together to get better average readings than either one alone. With Impedius' signal space multiplexing, we imagine a future with richer passive input devices that do not rely on either time or space multiplexing.